Let's apply our curve fitting technology to the results of another experiment. What we're going to do is to fire an arrow at a target. So as we notch the arrow on the bowstring and we pull the arrow back, getting ready to release it, the arms of the bow are bending, and this is sort of another example of a very powerful spring at work. And when we release the arrow, it will fly to the target. And what we've done is we've taken a bunch of measurements. So as the arrow flies up and then falls back down and hits the target, we're going to be measuring the height of the arrow at various times during its flight to the target, and working to fit a curve to that, so you can come up with a mathematical equation that describes the flight of the arrow. We'll also be looking into ways of measuring how well our curve is actually fitting the data. Up to now, we've been sort of eyeballing it, which was a good start, but we can actually develop some sensible mathematical measures that will tell us about the goodness of the fit.
Here's some Python code that lets us experiment with the data we got from firing the arrow with the bow. As before, we have a procedure that helps us get the data out of the data file and put it into a bunch of lists. In this case, what we have is a bunch of distances at which we made the different measurements, and then for each distance we have the heights at that distance from 4 separate experiments. To actually do the curve fitting, here we have tri-fits, which is very much like the routines we've written before. We're converting the distances which were in yards into feet, and then we're going to process the 4 measurements from each of the experiments into one average measurement for the height at that distance. With that in place, what we can do is to go off and plot the actual observations, again as blue circles. That's what that little BO means there as the argument to plot. And we're going to use polyfit, as we have before, to do a linear fit to see if there's a linear relationship between the distances arrow has flown and its height above the target. Okay, so we're all set to go. Let's save this out and then run it and see what the plot looks like. So here we have the data. You can see it as the arrow flies from the bow over here to the target, and the target looks to be about at 1,080 inches from where it was released. You can see it follows a trajectory where it goes up and then it comes back down again. And here's a linear fit of a line to that data, and it's probably fair to say that the hypothesis that the arrow travels in a straight line from the bow to the target is not a good hypothesis. You can just see that this linear fit seems to really bear no relationship at all to the actual data points. So let's go back to our code and let's try a parabolic fit. And so what we're going to do is look for a quadratic equation that relates the distance to the altitude of the arrow. So let's get this code back into execution. So this is just an addition of fitting a second degree equation to the data. And let's see how that goes. So we're going to save this out and run it again and look at the plot. And yes, oh, here we go. So this curve here actually looks like it fits the data pretty well. The jaggedness comes from the fact that we're just simply plotting the parabola only at the data points at which we actually had measurements. It would be possible to plot the parabola using many more values. Since it's a mathematical model, we could choose other distances that we didn't make measurements at, and then the parabola would look much more smooth. So that looks like a pretty good fit. And so we're sort of happy with that. Maybe what we should do, though, is to think a little bit about how do we measure the goodness of a fit. Is